These are formulas for what are called z-scores. I want to take the data that you have right now in your calculator or in your computer or I have on the board, and I want to calculate a z-score. So, like I said, my daughter had me take her temperature. Should we do it the temperatures? No, we'll do it here. I drive my car into the emissions thing, and tell me what my readout is. Well, suppose my readout is 10. That's not good, is it? See, if I get a readout of 10.0, let's say, 10.0 tons of emissions per year, we can find a z-score corresponding to x equals 10. So all I do is I use these formulas. Z is x minus x bar over s. So what goes where? Well, my x, we said, is 10. That's the data point that I just observed. Did we compute x bar for this data already? We did. 7.6, right? And now we divide by what? The standard deviation. Did we compute the standard deviation for this data? What did you guys get? 0.858 or something like that? Okay? So I can compute this and see what I get. So back to the calculator. Let me do. Let me see if I can quit this. Okay, so let me clear this up and do 10 minus 7.6. By the way, when you do 10 minus 7.6, what do you measure? 2.4. That's how far away my data point is from where? From the mean. Okay? So that's nothing fancy. The z-score is nothing fancy. You subtract to see how far away you are from the mean. And then I'm dividing by what? The standard deviation. So what's that give me? 2.79. What does that mean? It means how many standard deviations you are away from the data. So if you have 10, that's 2.79 standard deviations away. That's what your z-score is. So a z-score is the number of standard deviations away from the mean. So what do you think? Is 10 an unlikely thing to have happen? According to this, yeah. Okay, so that's pretty easy. By the way, the second formula, don't have this drive you crazy. These are Greek letters, and they're used if you're talking about a whole population. Can you guys even read this? This is x minus, does anyone know that Greek letter? It's called mu. The Greek letter M stands for mean. Mu for mean, okay? I mean, they did some common sense here. They said, well, let's call that mean. This one is called sigma, which is taking the place of what? S, okay? Yeah, it's the standard deviation also. But if you have a whole population, that's the formula, and we'll come back to that. For our chapter we're in now, the formula above is what we're going to use. Yeah, Jim?
What's the quantum variance?
So, okay, good question. The variance is what you get in the standard deviation formula if you didn't have the square root sign, right? S squared would be, I guess, this. So, you know, you could compute it without taking any square roots. Well, It will also tell you how spread out the data is. Okay? And I guess I have to compute it with you to show you how. Okay? Let's put it this way. If the standard deviation was 3, what would be the variance? 9, because that's 3 squared. If the standard deviation was 1,000, what would be the variance? 1,000 times 1,000 is 1,000,000. If the standard deviation was 0, what would be the variance? 0. Now, the only way that could happen is if you had the same data point over and over again and it never varied. Okay? It's really almost measuring the same thing. It's just different units if you want. You take the answer and square it. Or take a square root. Yes, David?
For x, just the normal x.
Yeah.
Just a number.
That could be any number that you put in there. Right.
And then n is all numbers.
N is the sample size, it's called. Yeah, how many data points there are. Okay. Now, yeah, this idea of interpreting z-scores, this is in your book. But again, things are unusual if you're more than 2 standard deviations away. That's the basic idea. I'm going to skip problem 8. Okay, I want to talk about percentiles. How many have heard of percentiles before? I scored in the 45th percentile. Whatever that means. Well, actually, what would that mean? If I scored in the 45th percentile, that means I scored better than 45% of people that got a score, right, took a test, let's say. Okay? If my height is in the 10th percentile, that means I'm taller than 10% of the people in my population. If my godson is in the 99th percentile for height, well, he's taller than 99% of the people his age. Okay? I don't know what they feed him, but that's what it means. So notice we're saying here there are 99 percentiles, 99 little marks that divide the population up into 100 groups with about 1% of the values in each group. Okay? Now, your book is also going to talk about, how do you find the percentile of a given data value? This only works if you have the data ordered. If you have the data ordered. And so maybe as an example, what I should do is let me take that Excel worksheet that we have on the computer. Here. Here are some data values we have. Remember this worksheet? And so here we're talking about car emissions, right? Now I can order the data by hitting the A to Z button. So if I hit home, where is it at? I guess I'll hit data. There it is, A to Z. And if I hit the A to Z button, it sorts it for me, which is really nice. By the way, that's very convenient if you wanted to find, say, the median. What's the median? I guess 7.3, right? Because it's halfway between 7.2 and 7.4. But it's helpful for other things too. Because you might say, I want to find what percentile I'm at if I'm at 8.2. Okay. So what do I do? Well, according to my formula here, according to my formula, the percentile will be the number of values less than x divided by the total number of values. And actually, it doesn't even have to be a value that's in the chart, but let's say it is. So let's say I have 8.2. Okay, guys, how many values are less than x? We're going to find the percentile How many values are less than x? Well, we have to look at the data, I guess, yeah. 6? If I check it out. Yeah, 1 through 6 are all less than 8.2. There are 6 data values less than 8.2. How many total data values are there? 8 times 100. Well, 6 divided by 8 is going to be 0.75. Okay? If I multiply by 100, I get 75. So 8.2 is in the 75th percentile. By the way, so is 8.0. If you had 8.0, how much of the data would be less than you? 6 of them, right? So you'd be in the 75th percentile. Yeah.
So if there's a data spot that's the same.
You don't count that. That's what I just showed. Yeah. Okay. Now, by the way, let me show you something here. 7.3. Can you guys find the percentile of 7.3 for me? Do that real quick. That should be quick. What's the percentile of 7.3? It's the 50th percentile. Do you guys see how that works? It means half of the data is, oh, what do you call it? It's also the median. So the median has another name now. It's the 50th percentile. So your book might write P50. And that's the median. Right? Is that okay? Because it means 50% of the data is below and 50% of the data is above. Okay? The median is in the 50th percentile. That's the right way to say it. Now, back to this. Yeah, they give you a big formula for, suppose I have the percentile and I want to find the data value. I think for now, I want to let you just kind of play with the formula for homework. It's not much harder than what we did. You can use the formula and go backwards. You could say, okay, what is the 70th percentile? Which data point does that correspond to? And this will walk you through it. This is in the book, so I am going to move on. Okay? But it's L equals K over 100 times N. That's not that bad. And then they even walk you through it. You'll find this. If you are having trouble using that formula when you do the homework, I'm just going to point out you will find this in the book, a flow chart that says, okay, here's how you do it. But let me point this out. Notice what step 1 is. Sort the data, right? Can you talk about percentiles if you don't have the data sorted? No, because you have to count how many are below something. So this A to Z idea is a good idea. Okay. All right. The book's also going to talk about quartiles. Well, Q1, Q2, and Q3 can split your data up into what are called quarters, right? And these numbers here are called the quartiles. And see, you also have a minimum data point, and you have a maximum data point, right? That came for free when I had the one variable statistics. And you've seen these before because they're computed by your calculator when you do the one variable stats. Let me go back and show you what the quartiles are for our data. So I'm going to go back to the calculator because it's handy. It's right there. Let me turn it on. Oh, I lost it. So I'm going to do it again. I'm going to do the one variable statistics again. Remember how I do it? We're going to hit stat. Yeah, let me move this out of the way for people that are still writing. And then what do I hit? Calculate one variable statistics, and I should put L1, but I don't have to. All right, right, so it gives me all that, but if I hit the down arrow, look what it gives you. It gives me min x 6.5. That's right here on the chart. It gives me Q1 7.15. It gives me, what's MED? Well, it's the median, but it's also Q2, and it's also P50. These are different ways of saying the same thing in a sense, right? Where you are on the order of the data. What's Q3 as a percentile? Well, I know it's 8.05 for this data. What percentile am I at if I'm in Q3? At the 75th percentile. Okay? Do you guys follow this? So it's kind of nice that I think that our book puts all of these in the same section, because it's really one big way of saying how is the data ordered. Percentiles, quartiles. And then once you understand this, then you can understand a new kind of plot called a box plot, or sometimes called a box and whisker plot. Has anyone ever heard of this before? If you haven't, I'll tell you that I showed you one today. I'm going to show you where. Let me find it. So let me open up my Microsoft Word, because I remember we used StatDisk, and it made some pictures for us, right? So this box plot is the graph right in the middle. And this was the data about the body temperatures, okay? So take a look, and I will tell you that all the information about the quartiles is contained in the box plot. You put a box around from Q1, which is 97.8, to Q3, which happens to be 98.6, okay? The middle 50% of the values occur in that box. Does that make sense? You take the median, which is the middle number, right, the 50th percent out, and you draw a line right in the box plot, and so the median of this data I can see is 98.4. Matter of fact, I could check that. Remember down below we had, StatDisk gave me a whole bunch of printouts. Where's the median? Yeah, 98.4. Remember that? Well, that's also on the box plot. So when they say a picture contains, all kinds of information, they weren't kidding. It's there. I have the median. I have Q1 and Q3. What's this 96.5, do you think? That's the minimum temperature that was, I feel bad for that kid. At a body temperature of 96.5. And then what was the maximum that was recorded? 99.6. So these must have been healthy people. I mean, no one had a fever, right? Question? So the box goes from Q1 to Q3, okay? So it contains the middle 50% of the data. The 25%, the quarter of the values that are above and the quarter of the values that are below, the median. So it gives you a nice bit of information here. Because if we look at the box plot, and then let's think about where the mean would be. The mean of this data, where does it appear compared to the box plot? Well, the mean is 98.2. So if you just went by the average, the mean, notice it's not right in the middle where the median is. It's kind of pushed that way, right? The mean is pushed that way. Why do you think the mean is lower than the median here? Talk to someone next to you about that, because we ought to be able to answer that. We've gone over that. Why is the mean lower than the median? I'll give you a minute to talk.